or the largest atom we know, which is oganesson, is the following. It's super long. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, and 7p6. Which would mean that in the outermost level, this means that in the outermost shell of the Bohr model, it would have 8 electrons. So if you wanted to instead express in order of increasing energy levels how many electrons are in each energy level, how would you do it? The answer is 2, 8, 18, 32, 32, 18, 8. So that means that in the 4th and 5th levels, because of the 4f and 5f orbitals, there are 32 electrons. We can confirm this by looking at the 5p, so the 4p and the 5p each have 6. And then add that to the 14 on each of the 4f and 5f orbitals to get 20 for each. Then add to the 4s and 5s to get 22, and then add by the 10 in the 4d and 5d to get 32. Really, if you can, and it turns out, by reading the electron, so the number, okay, but wait a minute. The S is the type of subshell. Now, if you want to draw the Bohr model of the atom using just the electronic configuration in the manner that I'm teaching you, rather than the one that I usually depict in my periodic table boxes, then the thing is that by reading the electronic configuration and knowing what it means, you can easily draw the Bohr model for any atom in the entire universe, rather than just searching an atom and needing to copy it down. No. For a problem, if they give you the electronic configuration of a certain atom between hydrogen and oganesson, you can draw the Bohr model for it by just reading the electronic configuration. Let's look at an example with 1s1, which is hydrogen. 1 means that there is one shell. So the number that is not a superscript, so just the regular one, is the energy level number. If it was a 2, it would be the second energy level. A 3, you're looking at 3 of them. 4, a 4th one. This goes up to 7, which means that there can be up to 7 electron orbits around the nucleus in the Bohr model. Then the letter doesn't matter because they all fill that energy level. S, F, D, and P, they're all the same energy level. So it doesn't matter when you're drawing the Bohr model. So when you're drawing the Bohr model, just forget about the letters. However, when you're drawing the electron configuration, you do need to know the order that I just told you. Now, the superscript numbers, how many electrons are in that orbital or subshell, not in the entire energy level. For example, 4f14 doesn't mean that for example, the electron configuration of lutetium ends with 4f14. But that doesn't mean there are 14 electrons in the 4th energy level. No. That is wrong, because what's happening this time is that the letters don't matter, but you have to sum the superscripts. So if you have, for example, 2s2, 1s2, 2s2, 2p2, which is carbon, there are 4 valence electrons. But how do I know that? Well, obviously I know that because carbon is in group 14, but if I didn't know the group numbers, like in this periodic table, how would I know? If I didn't have group numbers or the orbital things, actually, I did need the orbital thingies, but how would I know? The answer is, the reason is that I sum the superscript 2 on the 2s with the superscript 2 on the 4s, on the 2p, to get 4. So there are 4 electrons in the second shell, and the second shell is the valence shell. So you need to sum the subscripts of electron configuration segments with the same energy level to get the total number of electrons in that. It's a bit complicated, so let's just do another example, this time with the tellurium 2+ ion. The tellurium 2+ ion, or 2- ion, has, actually, tellurium 2- is the same as, that's literally the same as a, like a xenon atom. So we're instead going to keep things simple and instead just do the actual tellurium atom. So tellurium's electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. Oh, that's a very long name. But what happens now is this. Now let's try drawing the Borg diagram on my right. So what we do is we start with the nucleus, which we'll just represent by the symbol. Then you have the first energy level. This first energy level has 2 electrons in it because 1s2. And there's no 1 anymore, so we're done with the first shell. We're not done with the second energy level. Now for the second energy level, we have 2 plus the 6 on the other 2p, which means 8. Okay, so far so good. Now for all the 3's, we have 3s, 3p, and 3d. So we sum up the subscripts on each of them. So 2 plus 6 is 8. So here, plus 10 is 18. So far, with our first 3 energy levels, our Bohr diagram is starting to look like this. But we still aren't done. There are 5 energy levels in a tellurium atom, in a neutral tellurium atom. So what we're going to do now is we're going to count the number of electrons in the 4d orbital. Note that we're missing the 4f electrons, so there won't be 32 like there usually is. You don't always fill the entire shell before moving on to the next one. Not always. So 2 plus 6 plus 10 makes 18. So we also have 18. Fourth energy level, now our Bohr diagram is looking like this. Last energy level, the 6 plus the 2 plus the 6 is 8. So there are 8 electrons in the 5th or final energy level.